Okay, so Tuesday is the first test, and there's not a lot of material on it. So I guess that should make it easier to get ready for it. So hopefully, everyone will get off to a good start with scores. The topics are all the stuff on units, and then 1D particle kinematics, just numbers 2 and 3. And so, I mean, I know I've answered a lot of homework questions on this stuff already, but if anyone has any homework questions, uh, I'd be happy to answer them now. Anybody want to see any of the problems done or anything like that? Okay. Um, so today we're going back to material that's not going to be on the test. Um, so we were talking about, we defined position, velocity, and acceleration. And then at the end of last time, I gave these 3 equations that are going to be our ways of calculating relationships between these things. So last time, I introduced the 1D constant acceleration equations. And I'm going to just describe those again. So there are a bunch of variables in them. You have to know what the variables mean to make any sense out of this. But you have to choose 4 things in the physical world, the material world. The material world. Yeah, me too. That is good. Those are the only words I know, though. So those 4 things are, you have to choose the location that you're going to call position equals 0. You have to choose a direction that you're going to call positive. And once you do that, that by default defines the negative direction too. Oh, I just said I would talk about all that, and then like 30 seconds later, I forgot. Okay, well, so we have the test on Tuesday, and then on Thursday we have the quiz, one of the lecture quiz just at the end of class. So it'll take like the last 10 minutes of class on Thursday. I guess maybe I'll write something about that on D2L, put it up there. But to get ready for the quiz on Thursday, you just need to skim back over your notes, make sure you remember the big ideas, that kind of stuff. It'll be short answer questions about things I've said in class. Okay, so you have to choose the 0 position, the positive direction. Then you have to choose the instant that you're going to call time equals 0. And to use these equations, you have to define a 4th thing, an instant that you're going to call time final. And then based on those decisions, the variables p sub I and v sub I are the position and velocity at time equals 0 at the time equals 0 instant. P sub f and v sub f are the position and velocity at the time final instant. And then the equations say, so the first equation says v final is equal to v initial plus a times time final. The second equation says p final is equal to p initial plus v initial times time final plus 1/2 times the acceleration a times t final squared. And the last equation says 2a times the quantity p final minus p initial is equal to v final squared minus v initial squared. And we're going to use these equations over and over again. Those are the same ones that I gave you last time. And last time I showed how these get sort of a quick example of how these get used to solve problems. But now I'm going to give you a pretty detailed set of steps that I think it's a good idea, at least for now, to follow pretty carefully. Then later on, as you get more comfortable with this, if you want to take some shortcuts on it, that's fine. But these are just general steps for using the constant acceleration equations. The first thing you need to do is make those 4 choices that I mentioned above. So you have to choose a position equals 0 location, a positive direction, a time equals 0 instant. That's the instant that you click on the stopwatch. And then a time final instant. That's when you stop the stopwatch. These two are arbitrary. No matter where you choose the 0 position and what direction you choose is positive, you can still do the problems, okay? There are choices that can make the problem the math a little easier or whatever in a lot of cases, but there's really no wrong answer to this as long as you use them right. These two, though, getting those right is fundamental to everything that follows. If you choose those wrong, you can't get the answer you're looking for. And so these are, you have to be right. And the way you make those choices is these should be at instants where you're given information and where you want to solve for information, where you want to find information. Okay, so like in the example I did last time, what example did I use? Was it a ball rolling up a ramp or a car? That was before this. So the car, was it a car hitting the brakes maybe? Yeah. Okay. So in that example, I said I said the car starts out going 20 meters per second and it stops over a distance of whatever, 10 meters or 30 meters or something. And so where do we have information and no information? Well, we know information about the velocity of the car when it hits the brakes, and we know information about how far it's gone and the velocity when it comes to rest. Okay, so those are spots where we're given information and we want to find information. So those are always going to be our choice of time equals 0 and time final. Okay, time final is always later than time equals 0, so that defines it for you. But if you choose those, if you chose it to, like, you chose your time equals 0 to be like, oh, I'm going to choose when it's halfway there, and then I'm going to choose when it's 3/4 of the way to stop. Okay, you can't solve the problem no matter whatever else you do right, because you don't, that doesn't give you the ability to fill in information that you're given or to solve for the information you want. The second step is, so recognize here that in these three equations, there are only 6 variables that occur. Okay, there is time final, acceleration, P initial and P final, and V initial and V final. That's all the possible variables you could have. So let's just, for now, we're going to get in the habit of just going through those step by step. So out of all the possible variables, which are P final, acceleration, P initial, P final, V initial, and V final, which of these do you know values for? And which one do you want to find? In the car example last time, the thing that we were trying to find was acceleration. So A is the variable you're trying to find. The stuff that we knew going into it was, I think, P initial, P final, V initial, and V final. Okay. I usually list these out. Something, you know, you can do it however you want, but I usually list it out as like A is equal to whatever, P initial is equal to whatever. Keep going with the ones you know. And the thing you're trying to find is V final. You know, so just list out what information you have to use and what information you're trying to solve for. Okay, so now it's time to choose which of the 3 constant acceleration equations are useful, is useful. So what you want to do, the equation that will give you what you want is the one that, so look for the equation. It has to have the variable you're solving for. It has to be in there to solve for it. And every other variable in the equation is known. Okay, so you're going to be trying to solve for the variable you want. A single equation only lets you solve for one variable, so there can't be any other things you don't know in there. And then 4, well, you know, now you use this equation to solve for it. Sometimes there won't be an equation that works. That won't happen at first, but later on when we get into more complicated problems. If no equation works, then solve for another variable that you don't know. Usually the most useful ones are time final or acceleration. And then try again, you know. So you'll solve for this other variable, then you have another variable that you know, and see if you can use that now to solve for the one you want. Okay. So let me do an example. So let's say a ball gets rolled up a ramp. And as the ball passes point A, its speed is 2 meters per second. One second later, it reaches point B, which is 1 meter away. And we want to calculate two things. First, we want to calculate the acceleration. And second, we want to calculate the ball's velocity when it passes the point B. I'm going to start out with something that I think can sometimes be helpful. I'm going to draw one of those simple diagrams that we always draw in the problems like 2 and 3. So I'm not going to draw the ball in there. I'm just going to draw the 2 points, the distances. We'll figure out what stuff we know. Okay. So you don't have to do this, but I'm trying to sort of bring together how this topic matches up with the last topic that we did. All right, so we know that the ball starts here and goes to here. Okay, those are the 2 points that we care about. This is the point A, and this is the point B. And we're given that the distance between those two is 1 meter. And we're told that the elapsed time here is 1 second. It takes 1 second to get from A to B. Okay, and now we're going to do the first step in the constant acceleration equation steps method. We have to choose our position equals 0, our positive direction, our time equals 0 instant, and our time final instant. And once we choose those, we can start putting labels on this stuff. Okay. All right. Well, what do you want to choose as position equals 0? A? Yeah, why not? We don't have to, but that's probably what most people would do. So we'll call that 0. And what do you want to call the positive direction? Up the ramp or down the ramp? Okay. So that's the positive direction. All right, so P equals 0 is at A, positive direction is up the ramp. Those were arbitrary, but now we have to be careful about these two. We need to choose the instance that we're looking at to be the places where we're given information and where we're looking for information. So what do you want to call time equals 0? Yeah, we want to call time equals 0 when the ball crosses that point A, because we know stuff there. We know the distance between where the ball is at that point and B, and we know the velocity at that point. Okay, so this is going to be when the ball passes A. And what do you want to call time final? Yeah, passes B. And now based on these choices, okay, so if you start at 0 and go 1 meter in the positive direction, what's the position at B? Yep, positive 1 meter. And we're calling time equals 0 when the ball is at A, so this is 0. And so 1 second after 0, what does the stopwatch say? Yep, 1 second. And if you notice here, we're given a speed of 2 meters per second. That's not a velocity. In order to make that a velocity, we have to include directional information. But now that we've chosen the positive direction to be up the ramp, is the ball's velocity positive 2 meters per second a day or negative? Positive, yep. Because it's moving in the direction that we chose as positive. So now we'll list out these variables or go through these variables. Let's see, I'm gonna call this step 1. And now step 2, I'm just gonna go through this list and sort of like checklist. Time final, A, P initial, P final, V initial, and V final. And I'm gonna put them either in the column of stuff we know, or stuff we want, or neither. And we're going to do these one at a time, so I'm going to start by trying to calculate the acceleration. All right, so time final, do we know that? Okay, what's that? Yep, time final is 1 second. Now we get to A, do we know that? No, that's what we're looking for. P initial, do we know that? That's 0, yep. P final, do we know that? V initial, do we know that? Yep, that's positive 2 meters per second. And V final, do we know that? No, we're going to look for that for part B, but for now, we'll just leave that off. Okay. All right, and now we can look at that list of equations and figure out if there's an equation that has A in it. It has to have A if we want to solve for it, and every other variable in it is known. Well, you can just go through the list and check it. So the first one, it has A, so that's good. But then we don't know VF, so this isn't going to work. You can't solve for A if you also don't know VF. So that one isn't a candidate. What about the second one? Well, it has A, so that's good. We could solve for it. Do we know PF? Yeah. Do we know PI? VI? TF? VI we do. That's positive 2 meters per second. Do we know TF? Yep. So this equation will work. Sometimes more than one equation will work, but let's use this one. As long as it works, it doesn't matter. It is one thing you should watch out for is, I suppose, if you ever have the option of using the first one, that one's easier because you don't have to deal with squares and quadratic formula and stuff. Sometimes we'll see that some equations we need to use quadratic formula for. The first one never has that problem, but that's just a minor math problem. It's not like a thing about whether you can use the equation or not. Okay, so the equation we're going to use is PF is equal to PI plus VI TF plus 1/2 A TF squared. And we'll just start filling this stuff in. And by the way, for one-dimensional kinematics, I want you to keep the units in your calculations just to see how it works. Later on, you'll be able to skip that step. But for now, I'm going to put units in all this stuff. So PF is 1 meter. PI is 0. VI is 2 meters per second. TF is 1 second. And then we have 1/2 times A that we're trying to solve for times 1 second squared. All right, so I'm going to multiply these things out and see how the units come out. So here we have 1 meter. We can forget about that 0. That just goes away. But to multiply these two, you can think of that as 2 meters per second multiplied by 1 second. And for this one, you can think of it as 1 over 2 times A. 1 second squared is times 1 second times 1 second. These seconds cancel out. And so we get 1 meter is equal to 2 meters plus 1/2 seconds squared times a. Now I can subtract 2 meters from both sides to get this term with a in it by itself. So 1 meter minus 2 meters is -1 meter is equal to, and actually I'm going to rewrite this back out as 1/2 times seconds squared times a. And now I'm going to divide both sides by 1/2 times seconds squared to get a by itself. Remember, dividing a fraction is just multiplying by the reciprocal. So this is 1 meter. And I'm going to multiply that by 2/1 seconds squared. Anybody have any questions about what I'm doing with the division there? Yeah. Okay. So I'm just trying to divide. So first I subtracted 2 meters from both sides, and then we have -1 meter is equal to 1/2 seconds squared times a. And then I'm just trying to divide both sides by 1/2 seconds squared. But dividing by a fraction is the same as multiplying by that fraction's reciprocal. So I just multiplied both sides by the reciprocal of that, which is 2/1 with seconds squared now in the denominator. And that's what it looks like if I write it all out in that form that we use for unit conversions. And we get you multiply those numbers all out, you get -2. And notice that this is cool, if you multiply those units all out, you get meters on top, seconds squared on the bottom. And so if you do this right, the units that you get in your answer will always come out to be the correct units for the variable you're trying to solve for. Okay? Sometimes this is a nice thing to do because you can find mistakes sometimes. If your units don't come out to be the right ones for acceleration in this case, then you probably did some kind of multiplication wrong, and your answer is probably going to be wrong, you know? So a in this case is equal to -2 meters per second squared. Any questions about that? Okay, so -2 meters per second squared. So now let's go back up to this picture. We got an acceleration that's negative. Point in the direction of the acceleration. Okay, one person did it. Good job. But our positive direction we chose was that way. Our velocity was that way. The acceleration is negative, so it's this way. And that makes sense with the way we talk about acceleration and velocity, because we know this ball would be slowing down as it rolls up the ramp. So acceleration and velocity have to be opposite directions. Okay? Any questions about that? Okay, so now let's go on to part B. We're trying to calculate the velocity of the ball when it passes that point B. One thing that's sometimes useful is if you use the same 4 choices for a second part of any problem, so if you still have the same 0 position, positive direction, 0 time, and time final, then all the values you knew before for the earlier part are still true. They still keep the same value. So the question that you have to ask yourself is there any reason that we have to choose any of those 4 things different? The answer is no in this case, because we still want to find stuff that's at one of those 2 points. And yes? We'll do some examples like that. You could do it. If you change the position, certain values will change that you solve for. If you change the direction, the positive direction, then the signs of everything will switch. But if at the end you went back and used your signs and your position to point to things, what's this position, what's the direction of the velocity, direction of acceleration, they all physically mean the same thing. They just are different numbers. Okay, so let's keep the same 4 choices. And that means that we still know all the stuff we did before. So we still know time final is 1 second. We didn't know the acceleration before, but now we do. The acceleration is -2 meters per second squared. The initial position is still 0. The final position is still 1 meter. The initial velocity is still +2 meters per second. And we don't know the final velocity. That's what we're looking for. Okay, so of those 3 equations, can you find one that has VF in it and everything else in it is known? Well, if we try them in order, the first one works. This one works. And that's the one we want to use if possible anyways. V final is equal to V initial plus A times final. So V final is equal to 2 meters per second plus -2 meters per second squared times time final, 1 second. So V final is equal to 2 meters per second plus, I'll write this out as 2 meters over seconds times 1 second. This second cancels with this second. And so V final is 2 meters per second minus 2 meters per second. So 0. And so that point B is exactly where the ball comes to rest before it starts rolling back down the hill the way it came. Any questions about that? All right, let's try to do something with this. Let's try to draw a graph of position versus time. The way we did this stuff in lab. Okay, so positions on the y-axis times on the horizontal axis. The positions that are going to matter to us are, what are the positions? There's two positions that we know. 0 and 1, yep. And what are the times that matter to us? Yeah, 0 and 1 second. And we know that the graph is going to go between 0, 0, because at 0 seconds, it's at 0 position, and 1, 1. All right, so now, how is this going to be filled in? Well, remember that, so we know the two velocities, and we know the acceleration. And what we did in lab was we knew that the slope of this graph at an instant, the slope of the tangent, represents the velocity, and the concavity represents the acceleration, right? Okay, so the velocity at 0 seconds, what's it gonna, what's the velocity at 0 seconds? Positive 2 meters per second. Okay, so that's gonna be the slope. It's gonna be positive with a positive slope with a magnitude of 2. And the acceleration is -2. So is it gonna be concave up or concave down after that? Okay, so it's going to start out with a positive slope. It's going to be concave down. And what's the slope going to be when it gets to this point 1, 1? It's going to be horizontal, exactly. So at this point, it's going to be horizontal. At this point, it's going to be +2. It's going to be concave down. So that's the position versus time graph. Any questions about that? Who thinks you're ready to try something like this, talking to the people next to you? I mean, if you have smart people next to you, you're good. Okay. All right, so here's what we're going to do. We'll see how far we can get on this. But let's do the same problem. I know that feels like sometimes a little boring, but let's do the same problem. But we're going to make different choices about the 0 position in the positive direction. Time equals 0 is still going to be when it passes the point A. Time final is still going to be when it passes B. There's no way around using those 2 points. We can't change those. But what we're going to change is P equals 0 is going to be at B. The positive direction is going to be down the ramp. Okay, and that's going to change all of the variable values. Okay. So see if you can calculate the acceleration. Okay, first of all, let's see if we can think about what we're going to get. So remember, in this first case, with our first set of choices about P equals 0 and positive direction and stuff, our velocity was this way, right? Our acceleration was this way. that physically is what happens. You know, the velocity is this way, the acceleration is this way. So now that we have our positive direction down the ramp, that velocity that's up the ramp is going to be negative. Okay, it's still slowing down. So what's going to be the sign of the acceleration? Positive. It has to switch signs now because we changed what positive means. Okay, but the answer we're going to get is going to be positive 2 meters per second squared. It's going to have the same magnitude. It's just going to change directions. Okay, so if you don't get that, something went wrong. But see if you can go through, and please, you know, at least for now, go through those steps. You can look at the steps as you do it, but just get in the habit of going through all these steps. And work together, see if you can get this answer. Ask me questions if you get stuck. And after pretty much everybody's had enough time to think about it, I'll go through it. And you can, at that point, compare your steps, make sure you're doing everything at the right time. Okay, so just like the problems where you have the house and the boat and the fish and the I'm gonna draw out the stuff that we don't control, you know, and then just a little diagram of the motion, and then I'm gonna put our choices on here. So the ball still starts at this point A and ends up at this point B. The motion looks like this. It goes from A to B. And we know the distance between these two is 1 meter. We don't have any control over any of those things. Oh, and we also know that the elapsed time here is 1 second. And now we're going to put our labels on here. So we still, our zero time is still going to be when it passes A. So this is still 0. And 0 plus 1 second is still 1 second. So the time labels didn't change. But this time, our 0 position, we're putting at B. And our positive direction is down the ramp. And so if you start at 0 and go 1 meter in the positive direction, what's the position at A? It's positive. Because just always think of starting at 0, and if you go in the positive direction, it has to be positive, and if you go in the negative direction, it's negative. Since our positive direction is down the ramp, what's the velocity of the ball at point A? Negative 2 meters per second because it's going up the ramp. Okay. So now let's list out the variables and we'll figure out what we know and what we want. Do we know time final? Yep, that's still 1 second. Do we know acceleration? That's what we're looking for. Do we know the initial position, the position at time equals 0? What's that? That's positive 1 meter. Anybody have any questions about that? Do we know the final position? That's 0. Do we know the initial velocity? That's negative 2 meters per second. Anyone have any questions about why that's negative? All right, and final velocity we don't know. So now we're looking for an equation that works with these. And the one that works is the same one that worked for part A last time. P final is equal to P initial plus V initial times time final plus 1/2 A times time final squared. So now substituting these in, we get 0 is equal to 1 meter plus -2 meters per second times 1 second plus 1/2 times A times 1 second squared. And so 0 is equal to 1 meter, and now I'm going to write this out as -2 meters per second times 1 second. You can see that those seconds are going to cancel and we're left with meters. That's good because you can't add quantities that don't have the same units. And then plus 1 over 2 times A times 1 second times 1 second. And so we get 0 is equal to 1 meter plus -2 meters. I'll just write that as -2 meters plus 1 over 2 times 1 second times 1 second. And then all this is multiplied by A. Okay, you can think of it as like we're going to have to divide by all that stuff in parentheses to get A by itself. Add these two together and you get -1 meter. And then I'm going to move that over to the other side or add 1 meter to both sides. So we get +1 meter is equal to 1 over 2 times 1 second times 1 second times A. And the last step is to get A by itself. We're going to multiply both sides by the reciprocal of all this stuff multiplied to A. That's dividing by it. And so we get 1 meter times 2 over 1 second times 1 second. And this is equal to A. And we get that A is equal to +2 meters per second squared. So we got the same magnitude of acceleration, but the opposite direction. Does it make sense that we got a positive acceleration? Yeah, because the velocities are negative now. It's slowing down, so acceleration has to be positive. Yes? Okay. What I want to do, so think of this, if instead of this messy thing, I just had 4A. To solve for A, I want to divide by 4, both sides, right? You know what I mean? If this is just, if we just had that 1 is equal to 4A, then we divide both sides by 4 to get A by itself. So we're doing the same thing. We're just dividing by all this stuff. It's just that it's messy now. It's not 4. But dividing by a fraction is the same thing as multiplying by the reciprocal. So I multiplied both sides by 2 over 1 second times 1 second. Let's plot this out. So here's the position versus time graph. What are the times that matter in this example? 0 and 1 second. What are the positions that matter? 0 and 1 meter, yep. Okay, at time equals 0, what's the position this time? 1 meter, positive 1 meter. And is the velocity positive or negative? Negative, yes. And at time 1 second, what's the position? 0, so that's here. And what's the velocity there? 0. Well, we haven't calculated that yet, but it will be. I forgot to do that. So we know that the slope is going to be 0 here. Okay. We know the slope is -2 here. The acceleration is positive. So is it going to be concave up or concave down? Concave up. Positive is concave up. Negative is concave down. And so the graph looks like this. Okay. So it's shifted because of our new choice of the 0 position, and it flipped because of our new choice of the positive direction. See the connection between this stuff? And it's kind of piggybacking on the stuff that we did before this. You have to understand how those choices of the 0 position and positive direction and stuff affect the variable values in order to be able to calculate the numbers with these constant acceleration equations. Okay, anybody have any questions right now? Okay, have a good weekend. See you Tuesday. So don't forget to get ready for the test.